Back in the year 1202, a man in Pisa asked a silly little question about breeding rabbits. And hidden inside his answer was one of the most famous numbers in all of mathematics, the golden ratio. Watch how it falls out almost by accident. Here are the rules. You start with one pair of baby rabbits. It takes them 1 month to grow up. And once they're grown, every single month, they produce one fresh new pair. Nobody ever dies. So how many pairs do you have after a year? Let's just count month by month. 1 pair. Still 1 while they grow up. Then 2, the first babies arrive. Then 3. Then 5. And the pattern is already staring at us. Each number is simply the sum of the 2 before it. This is the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, 21, and on it goes. And the rule that makes it is beautifully simple. The next term equals the sum of the previous 2. Now here's the key idea for cracking a rule like this. When each term is built from the ones before it in a straight, linear way, the natural guess is that the sequence grows geometrically. So let's just try. Suppose the nth term is some number lambda, raised to the nth power. Plug that guess into the rule and you get lambda to the n plus 1 equals lambda to the n plus lambda to the n minus 1. Now every term shares a common factor, lambda to the n minus 1. Divide it out and all those powers just vanish. And what's left is astonishingly small. A plane quadratic. Lambda squared equals lambda plus 1. This is called the characteristic equation, and it holds the whole secret of the sequence in 3 little terms. Solve it with the quadratic formula, and out come 2 roots. 1 plus or minus the square root of 5 all over 2. The plus root is about 1.618. The minus root is about negative 0.618. And that first root? That is the golden ratio. Mathematicians call it phi. 1 plus root 5 over 2. The very number that shows up in art, in seashells, in the spiral of a sunflower. It was hiding inside a puzzle about rabbits the whole time. Since both roots solve the equation, so does any blend of them. Match the starting values, do a little algebra, and you land on something remarkable. A single closed formula for the nth Fibonacci number. It's called Binet's formula. And here's the part that feels almost like a magic trick. This formula is stuffed with square roots and irrational numbers. Yet plug in any whole number n, and every bit of that mess cancels, leaving a perfect integer. 1, 1, 2, 3, 5 every time. Now look closer. The second root, negative 0.618, is smaller than 1 in size, so raising it to a high power shrinks it toward nothing. It just fades away. Which means, for large n, the Fibonacci number is essentially phi to the n, divided by root 5. The rabbits grow exponentially, with the golden ratio as their base. And that's why, as you march down the sequence, the ratio of each Fibonacci number to the one before it homes in on the golden ratio itself. A question about rabbits, a tiny quadratic, and out drops one of the deepest numbers in mathematics. Sometimes the whole answer is hiding in the shape of the rule.